Okay, so the purpose of this lab is we want to investigate the relationship between normal force and the force of friction. So those will be the two things that we will be measuring actively throughout the lab. Okay, the way the lab will work is that on each trial, we will add more mass to our friction sled. By adding more mass, we also change the weight of the sled. And as a result of changing the weight, we change the normal force as well. Okay. On each trial with a different mass, we will also measure how much force is required to overcome static friction. Okay. So on each trial, we'll be measuring the force required to overcome static friction. In other words, we'll measure the force of static friction in each trial. Now, when we do this lab, a couple of things we need to watch for. We're going to be doing this lab on the floor, okay? Your desks are too slippery for this lab to work. Also, they're not level, so they're not a good surface to use. So what we have to do is we have to make sure that anything that can affect friction is at least at best somewhat controlled. Right? So if we're using the floor, okay, we need to consider the nature of the floor. If I drag a sled along the floor, what does it do to that piece of floor? If I drag something along a section of floor, what will I find usually in a pile along it or under it or whatever afterwards? Dirt. What has the sled just done to that piece of floor? Cleaned it. Can I use that piece of floor in the next trial? No, it's now different than the rest of the surrounding floor. So my suggestion to you would be that we need to assume all parts of the floor are uniformly clean/dirty. Okay, and that I would use a different floor tile on each trial. You're not pulling the sled very far, you're just pulling it till it moves. Okay, it's going to move like this far, and then that'll be it. That'll be it. Okay, so pick a series of 4 or 5 tiles, and on each trial, put the sled on an adjacent tile. That way we can assume that those 4 or 5 tiles were about the same in terms of cleanliness or dirtiness at the beginning of the lab. Is there an even better way to make sure that they are? Yeah, just give them a quick wipe. Okay, you can go and grab a paper towel from the bathroom, give them a quick wipe, and then, okay, good. Now I know that all of those pieces are the same. Okay, something at least about them is the same that affects friction on every trial. Do you get the hint here? I'm trying to give you some controlled variables without giving them to you. Okay, now, other things that we need to be careful of is the direction that we pull. Okay, when this is set up, okay, you can see in the picture there that they've got, there's a string on the front of every one of these friction sleds. Okay, these are high-tech, okay, constructed friction sleds by Mr. Dickey and myself. And we use the handyman secret weapon, duct tape. Okay, that's the handyman secret weapon. You guys are of a generation who doesn't know who red green is, but he's like a Canadian icon. Okay, so women don't find you handsome, they should at least find you handy. And duct tape is the handyman's secret weapon. Okay, so what you're going to do is hook the force meter onto the string, and everything is going to be on the floor, including the force meter, flat on the floor. That way, we don't bring any angled forces into play. Okay, if I pull up like this, did we see what effect that would have in a question we did the other day? Right? We don't want that. Okay. Conversely, I don't want to pull to the side too much either, or downwards, because that could have the opposite effect. Okay. I want to make sure I'm pulling as straight horizontally forward as humanly possible. Okay. So that I don't alter any forces. Okay. Especially normal force. Everybody follow there? Okay. I think you guys can come up with a couple others. All right. So that's the only pieces of equipment you need. Okay. So you need the friction sled with the masses, the force meter, and the Bluetooth transmitter that you've used before. Now, so that kind of takes care of the design. Okay, for the hypothesis part, okay, your if part needs to talk about what we're studying in this lab. Okay, and that is the relationship between normal force and static friction. So the if part should tell me what their relationship is. Okay, and by that I mean, is it polynomial? Is it linear? Is it exponential? Okay, that kind of thing. Okay, what kind of relationship do they have? Okay, is it directly proportional, inversely proportional, whatever you decide? Okay, that's the if part. Okay, the and part, as always, describes the experiment. Okay, the then part needs to tell me this. How will you calculate mu from a normal force versus force of friction graph? Okay, we're going to build a graph with our data, and it will graph normal force versus the force of friction. Okay, remember the manipulated variable always goes on the x-axis. This is the first lab we've had where time was not the manipulated variable. All right, so you have to decide which one of those forces are you manipulating, which one goes on the x-axis. All right, so that's your hypothesis. Okay, as we said, for the procedure, you're going to have this type of a setup. Okay, when you hook up to the Bluetooth sensor, it will give you two options for what sensor you want to use: force push positive or force pull positive. Okay, select force pull positive. It should make all of your values positive when you pull. Okay, if it doesn't, it's not a big deal. If you get all negatives, we'll just make them positive and it'll still work. Okay, so you're going to select force pull positive on that one. Okay, so set it on the floor, and for your first trial, the sled will be empty. Okay, so the sled will be empty on the first trial, and that's going to be an easy pull when it's empty because there's not a lot of mass there. Okay, so when you pull it, okay, and it's on the floor, obviously it's not on the floor here, but this is where you can see it. Okay, so the lab will work like this. You got to like just keep it tight, okay, and then very gradually increase the amount of force you apply until it slides. Then you're done. That's trial one. Okay, but if you just go, all right, we're connected, and give it a yank, you're not going to get good data. All right, you have to very, very slowly increase your amount of force. Okay, ever so slightly, ever so slightly, ever so, and then it slides. Now I'm good. Okay, it does have to. You have to be very careful about that when you are doing this lab. Okay, otherwise you won't get good data. Do that for each successive trial, and I believe that in your analysis here, okay, you're going to have the mass in kilograms, okay, the normal force, which in this case will be equal to the force of gravity because it's a level surface, okay, and then this is the one that you're going to get from the force meter. All right, so all you're going to get from your data, so when it spits out the table, is just go through the table, watch it go up, 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 and then pick the biggest value. After that, it doesn't matter anymore. Okay, all you need is the biggest value for the force of static friction and put it in here for each trial. Okay, then you will use this and this to build a normal force versus force of friction graph. Okay, from there, you will calculate mu. Right, there is a way to get mu from that graph. All right, so in the analysis here, okay, so it'll say include your graph here along with your calculation of the coefficient of static friction. So show me that calculation and then justify and explain why that calculation accurately gives you the coefficient of friction. Okay, for your conclusion, so copy and paste your hypothesis, explain why your data supports it or not. Okay, sources of error, if there are any, well, there are some, so list two, okay, and ways to fix them, and you don't have to do the class discussion. We'll talk about that when I hand them back. Any questions on what you're doing? Okay, one thing here, actually a couple things here. The mass of the cart, okay, or sorry, not the cart, should say sled, okay? The sleds are 0.254 kilograms when they are empty. All right, so they are 0.254 kilograms empty. So your first trial will be 0.254 kilograms for your mass because you're just pulling an empty sled. Okay. So actually, let's maybe just kind of fill that in right now. So we got 0.254 kilograms, okay, for our first one. Okay, for your second trial, okay, we're only doing, Okay, we've got 6 trials in here, but there are 6 masses. So your second trial is going to be both the 10-gram mass and the 20-gram mass put in there. If you just put in the 10-gram mass, it doesn't make enough of a difference, okay, in the normal force to affect the force of friction. So your second trial will be the sled and 30 grams. So it'll be and so on, okay? Just keep adding masses till the sled is full, all right? And that will fill up all of your slots, okay? Okay, in terms of your graph, okay, make sure you've got your, on your app, the graph will look kind of like this. It'll have time on the x-axis, okay? Obviously that's not what we're graphing because it's just showing you what the maximum force of friction is, okay? Just kind of watch it when it spikes, you're good, and the cart starts to move. Then in your actual data chart, just look for the biggest number, all right? You actually you won't use this graph at all. Okay, the one that it shows on the screen you won't use. Okay, we're just going to pull the maximum value out of there, okay, and use it in the chart to build a normal force versus force of friction graph. Okay, I think that covers all of it. So you can get together with your group. Okay, we've got lots of sensors, lots of sleds. Okay, so groups can be smaller. Just make sure everybody's got a group, and you can get started.